It's about 9 o'clock, 8:30, 9 o'clock at night. As the relative humidity starts to increase with the nightfall, it's a great time to harvest water out of the air. And I'm about to show you Hope Waterworks Video 2, which is a 6,000 BTU pre-production prototype designed after patented technology that harvests water out of the air. As we walk through past the thing, you can hear it running there. It is a pre-production prototype, so it's inside of a case that's designed to have an engineering production group take the sides off and look at the actual machine itself. But as you can see, the machine has been running for about 10 to 15 minutes now, and for a 6,000 BTU machine, the water is quite literally pouring out of the machine. This machine's capable of generating up to 40 gallons of water per day at an extremely low cost. In a minute, I'll walk you around the other side of the machine, and we're going to be looking at gallons produced per day at different relative humidities and temperatures. We're also going to be looking at liters produced per day at different temperatures and relative humidities. And then we're going to look at the cost per liter. The cost per liter is in kilowatts, so we'll look at a chart, relative humidity and temperature chart that tracks the the liters produced at 1 kilowatt. One of the things I have to tell you is this technology is sizable, and this particular unit that we're looking at today is a 110 volt machine at a 15 amp. It's plugged into a normal, or I should say an average household wall plug. This particular unit is the least efficient unit of the air to water machines, and we'll look at that when we look at the kilowatt or liters produced per kilowatt. As we go up in size with this technology, we get larger BTU outputs. A good example is a 60,000 BTU or a 5-ton unit. That unit is capable of producing up to 300 gallons of water per day. And as we plug into higher voltages, 220 as an example, single phase, or 220 three-phase, the efficiency jumps up quite a bit. And along with the gallons per day, the cost per gallon and per liter drops dramatically with the larger machines. But like I say, this machine is the least efficient, and even being the least efficient, it produces more gallons per day for the BTU size at an extremely low cost for this size. So we're going to walk around the side of the machine, other side of the machine, where I have taped some of the charts. Now the charts are based on lots of field testing, but it's measured in grains per pound and the airstream going through the machine. So we actually weigh the air going into the machine and the air exiting the machine, and we get the weight of the water generated. So the charts are extremely accurate because they measure the amount of water being extracted and water weight. So this is the first chart that we're going to look at. There's a definition of the machine up above describing it's processing 350 actual cubic feet per minute through the machine. The harvest rate of this machine is 25%. In other words, the airstream that's moving through the machine, we're removing 25% of the moisture that's in the air. As we go up in size in BTUs, we're able to extract 40%. That's another reason why the larger BTU size are more efficient. Then it describes here in the data there, it's 110 volt machine, 60 hertz, 15 amps, and that is at 1.65 kilowatts. That's constant runtime or constant kilowatts. And then we have of course, we have the water harvest rate stops at the dew points below 36 degrees. Water harvest guide is at sea level. So then we're going to walk down and look at the actual chart itself. Over on the left-hand side here, we have relative humidities. Along the top here, we have in yellow is the temperature in Fahrenheit. One of the things I like to show is this technology isn't affected by operation in high heat areas. In fact, it does better in high heat areas. The machine, unlike a standard air conditioning system, does not shut down when it's 80 by 80 degrees Fahrenheit by 80% relative humidity. In fact, it functions quite well right up to 100 degrees with 90% relative humidity. Now, one of the things I like to point out in this is 80 by 80 is a standard high heat load for an air conditioner, and we harvest. I show the harvest rates at that. If you look over here at 80% relative humidity, and then you come over here and look at 80% temperature, this particular machine produces 19 gallons of water at 80 by 80 in the course of one day. So like I said, that's extremely accurate in 1 to 2%. So that's that. But this machine will also produce, if you come up here to 100 degrees and you come down to 90% relative humidity, it will actually generate 41 gallons a day. So, and that's out of a 6,000 BTU unit. Now, a 6,000 BTU unit, as far as air conditionings are concerned, is about the size of a small window shaker. So it's extremely small machine that generates a tremendous amount of water for its size. So the next chart we're going to look at is right next door to it, and essentially this is water's harvested per day in liters. And once again, in liters, we look at the relative humidity here at 80%, and we just follow that relative humidity chart over to the 80% Fahrenheit right above there. And at 80 by 80, we're going to be generating 71.9 liters a day. So the reason for the liter chart, you can do the conversion in your head with gallons, but the kilowatt or the energy consumption is generally done in liters per kilowatt. So our next chart is the kilowatts per liter. And so it seems that we're using the 80 by 80 as a typical refrigeration heat load, or excuse me, air conditioning heat load. We'll do the same. We'll come down here to 80% relative humidity, and we'll go across the chart to 80 degrees. And at 80 by 80, this generates 2.86 liters per kilowatt. Now, the average kilowatt cost in the United States is 12 cents per kilowatt. So essentially, we're getting 2.86 liters for 12 cents. So if you do follow this up here and you go down to 90 degrees or across the top, it's probably easier sometimes with Fahrenheit. Go across to 90 degrees or 100 degrees and track this down to 90 degrees, then we're generating 3.91 liters per 1 kilowatt, or for 12 cents. So that's how that we do that. And like I say, this is the least efficient unit that we have, but for a 6,000 BTU unit, it puts out a tremendous amount of water for its size. So if there are any questions, then please send all the questions that you may have to Sean Sullivan, or attention Sean Sullivan, at Sean, SHAUN, at b4-labs.com. Thank you for watching, and please send me any question and all questions that you possibly have. One other quick note, we do have technology or other technology that we can put on this machine that measures grains per pound going in and out, and with that software we can install a real-time harvest rate right on the machine. So that's just an added note. But once again, any questions, please contact me at Sean, SHAUN, at b4-labs.com. Thank you.